Swayam Prabha. Digital India. Educated India.
So, we will continue our discussion on bending of circular plates subjected to axisymmetric loading. We have already seen certain points. So, let us just look at them once again. We have got the equation of the deformation in this form: d2 phi dx square plus 1 by x d phi dx minus phi by x square is equal to minus v by d, wherein this phi is nothing but slope, and this slope is related to the deflection by this relationship. Here the slope is negative. So, that is why it has become in that form. So, let us just try to again sketch a portion of the plate. So, this is the plate and this is our x axis, and starting from the center we have the z axis down, and under the action of the loading like this, we are going to see the deformation of the plate in this manner, and therefore, the slope is now going to be at any point the slope is like this. That is what is phi, and then phi is equal to minus dw dx, because we consider w to be this distance, that is the distance of the deflection of the center from the original position. Now, this equation, it is good to work with this form too, and you have come across this type of equation in connection with the thick cylinder. We had similar equation, and it can be written in a form so d by dx 1 by x d phi x dx is equal to minus v by d, and some of the variables that we introduced, it was m1 was moment per unit length of circumference, similarly m2 was moment per unit length of radius, and V was shear force per unit length of circumference. Let us now consider some specific examples. Think of a pressure vessel So, think of this pressure vessel with the end closure which is circular, and they could be fastened to each other by bolts, they could be, there can be welding as well. So, this type of, this portion of the plate is subjected to pressure loading like this. We can have some external force also acting, maybe some load coming up on this plate like this. So, this is a case of loading wherein we can now try to look into what sort of deformation this particular enclosure will undergo and what sort of stresses are going to come up. Now, the end conditions that are going to be persisting here. So, if you would like to consider that the plate is up to this much, then the end condition at these ends, they can be considered to be clamped, or they can be also considered as simply supported. So, we will like to consider both the cases. So, the conditions that can exist at this point and at this point, it can conform to clamped condition or simply supported conditions. So, we will now try to consider a general case. So, we have a situation like this, that the plate is, let us say, it is supported at the edges, and it could be simply supported or clamped. So, it could be clamped as well. So, let us write both the possibilities, and we will just go ahead as a general derivation. So, the loading is on the plate some normal load plus distributed load acting. Now, in order to find out the solution, we must know what is the shear force per unit length of circumference at a particular position. So, let us now consider a position which is at a radial distance of x. So, therefore, let us consider a circle . Say this is the circle of radius x, and if we now segregate this portion, we will have forces, shear forces acting on its boundary, and we can now write, if we consider that V is the shear force per unit length on this boundary, then in that case we can write now 2 pi x into V, which is going to act in the upward direction, and that is to be counterbalanced by P plus small p into pi x square. So, that is the force balance, and this force balance is going to give us the value of the shear force per unit length that we need, and therefore, V is equal to P by 2 pi x plus small p into x by 2. So, that is the shear force. We can substitute this value into the equation of governing equation of deformation of a circular plate, d by dx 1 by x d phi x dx is equal to minus 1 by d. For V we write P by 2 pi x plus Px by 2. Now, if this is easily integrable. So, if we do that, 1 by x d phi dx minus 1 by d p by 2 pi ln x plus p x square by 4 plus there will be one arbitrary constant of integration. So, that is C1, let us say. So, this is a constant. Again integrating once more, we get, or rather we can rewrite this expression in this form. P by 2 pi x ln x plus P x cube by 4 plus C1 into x, and if we integrate once more, this gives us phi x is equal to minus, this is the case of product of two functions. So, you can integrate this first, that will give us x square by 2 ln x, then minus x square by 2, differentiation of this will give us 1 by x. So, finally, we will have x by 2 and integration of that will give us x square by 4. So, we are going to get now p by 2 pi x square by 2 ln x minus x square by 4 plus p x 4 by 16 plus C1 x square by 2 plus another constant of integration will come, let us say that is C2. So, if we now write finally phi is P by 2 pi d, we have x by 2 ln x minus x by 4 minus pxs cube by 16d plus c1 by 2x plus c2 by x. So, we have got now the expression for phi, the slope, and now we can certainly go for finding out the deflection, since phi is related to the deflection by the formula phi is equal to minus delta w delta x. So, we can now consider phi as delta w minus delta w delta x, and therefore, this is of course for small deformation, because for small deformation we can write tan phi is equal to phi, and therefore, for small deflections we can write that, and hence we have dw dx is equal to p by 2 by pi d x by 2 ln x minus x by 4 plus pxs cube by 16d minus c1 by 2 x minus c2 by x. Therefore, w deflection is obtained on integration, which is nothing but capital P by 2 pi d, and integration of this is again a product of two functions. So, we will now get x square by 4 ln x minus x square by 8. From this we get this one, and this one will give us x square by 8. This will give us px4 by 64d minus c1 by 4 x square minus c2 ln x plus c3, wherein again c3 is a constant of integration. So, if we now combine the similar terms, we have p by 8 pi d x square ln x minus x square px4 by 64d minus c1 by 4 x square c2 ln x plus c3. So, this is the complete expression for W in the case of loading, where we have concentrated load capital P and distributed pressure P. Now, let us try to go for specific problem where the plate is clamped, and let us also consider that capital P is absent, there is no concentrated force, but there is uniformly distributed pressure over the whole plate. So, let us try to consider again the end conditions to be clamped, fully clamped plate. So, we have now a case, here it is clamped, further we have capital P equal to 0 and small p is not equal to 0, we can see that the boundary conditions are obvious. We will have deflection equal to 0 if the dimension of the plate is considered to be a, then at x equal to a, w equal to 0. Now, the expression for w that we have here, it means that if you try to calculate the deflection at the point x equal to 0, that is at the center of the plate, this term will shoot to infinity, but we cannot have infinite deflection at any point on the plate. So, for finite deflection everywhere, we must have this constant C2 equal to 0. So, for finite W everywhere, C2 equal to 0. So, that is one constant is resolved. Now, we will make use of the other boundary conditions to find out the constants. Other boundary conditions happens to be are as follows. We have the slope at the end of the plate x equal to a, that is 0. So, we can write now boundary condition that the slope dw dx equal to 0 at x is equal to a, and at the same time we do not have any deflection at x is equal to a. So, therefore, another boundary condition that we have already stated earlier is that w equal to 0 at x is equal to a. So, these two conditions are going to suffice to find out the two constants C1 and C3. So, let us now write dw dx. dw dx, we have only this part of the expression because this capital P is 0. So, therefore, it is going to be P xs cube, the 4 will cancel and we will have this minus C1 x by 2. Using the first boundary condition, dw dx at x equal to a at 0, we have P a cube by 16d minus C1 a by 2 equal to 0, and therefore, constant C1 is equal to P a square by 8d. So, that is the constant, first constant. Now, we can write therefore w as P x to the power 4 by 64d minus P a square x square 32 by 32d plus C3. So, that is the expression for w, and now w is equal to 0 at x is equal to a. So, from that if we put x is equal to a, then in that case we are going to get C3 to be equal to P a 4 by 64 d minus P a 4 by 32 d and that will give us C3 equal to P a 4 by 64 d. Finally, we have got all the constants, and now when you put this in this expression, it forms a quadratic, and therefore, we have w equal to P by 64 d a square minus x square whole square. So, that is the deflection of the plate. Now, we have to calculate, we are in a position to calculate the deflection very easily. It is obvious that at x equal to 0 we are going to have the maximum deflection, and therefore, W maximum we can write W maximum, and that occurs at W at x is equal to 0, and which is nothing but PA4 by 64 d. Now, we would like to calculate, our other interest is to calculate the maximum stresses. Deflection is resolved. So, therefore, let us now calculate the maximum stresses. For that, we must be able to calculate the maximum bending moment M1 and M2 at the critical location. So, for doing that, we will have to find out the radius of curvature, and therefore, now we will write phi as minus dw dx, and that is equal to minus p by 64 d to a square. So, we just make use of this relationship, and we have this multiplied by 2x, and that is nothing but p 16 d x into a square minus x square. So, that is the expression for the slope phi, and we can now write d phi dx is equal to p by 16 d a square minus 3 x square. So, we can write this thing as a square x minus x cube. So, that gives us d phi dx. We have the bending moment M1, which is in the xz plane, d into d phi dx plus nu phi by x. So, if we substitute the values, p by 16 d a square minus 3x square plus nu into phi by x. So, therefore, it is p by 16 d minus a square minus x square. So, d get cancelled, this d will cancel everywhere. So, it will become independent of d. So, we will have M1 equal to p by 16 a square minus 3x square plus nu into p by 16 into a square minus x square. Similarly, M2 is going to be given by d into phi by x plus nu times d phi dx. So, we can now write M2, which will have be like this, p by 16 a square 1 plus nu minus x square 1 plus 3 nu. So, M1 at x is equal to a, we see that the at x is equal to a, we are going to have the maximum bending moment. I am sorry, we will try to calculate the bending moment at x is equal to a. So, M1 at x is equal to a is equal to P by 16 a square minus 3a square nu into 0, and therefore, this is nothing but P a square by 8. Similarly, M2 at x is equal to a is equal to, here x is equal to a, so we will have this term cancelling, here it is nu and it is 3 nu, so we will be left with 2 and 2 will cancel with this 16. So, therefore, we will have nu P a square by 8. So, these are the bending moments at the end of the plate. Now, let us try to see how the stresses are going to come up. Because of this bending moment, we will have a stress which is given by extreme fiber stress, which is maximum, which is nothing but can be calculated from the formula 6 m by h square, because here b equal to unity. So, 6 m by b h square, b is unity. So, we can write now 6 m by h square, and since this is P a square by 8. So, we can now have this substituted here, and this will give us 3 by 4 P a square by h square. So, this is the stress. It is, if we consider the stress at the top fiber, that is the value top fiber. Likewise, if we calculate the maximum stress due to M2, sigma 2 maximum is equal to, it is simply nu P a square by h square. So, here in the value is this, and therefore, we will have nu P a square 6 times this divided by h square. So, that gives us, we will again have of course 3 by 4 factor will be there, and this is the stress at the top fiber. It is very important to see how these both the stresses are going to be positive at the top fiber. So, let us look at the plate which is circular. Let us now consider only a portion of it at the center, and I have drawn it here. So, this is the portion which is subjected to bending. So, because of the pressure acting all over, it is going to bend like this, and you see here that the curvature that is going to be here is negative, whereas the curvature here that is going to come up is positive curvature, and this is possible. The bending moment is acting like this. Already we have seen that M1 and M2 both are negative bending moment. So, this M1 at the end is minus P a square by 8. So, it is a negative bending moment and it acts like this. Now, under the action of this bending moment, we will have tensile stresses developed at the top, compressive stresses at the bottom. So, therefore, here you expect tensile stresses, and at the bottom we are going to get compressive stresses, and anticlastic curvature will develop such that since compression is here, there will be extension here and contraction at the top. So, the anticlastic curvature will develop, which is going to look like this. The plate is going to really it is going to deform at the edges like this. Since it is clamped, this sort of curvature cannot come up, and therefore, we will find that there will be bending moment developed like this, which is M2. So, this bending moment will try to develop like this to undo that curvature. So, therefore, this bending moment is negative, because we have considered the other direction to be positive bending moment. So, therefore, this is also negative bending moment, that is what has come, and under the action of this type of bending moment, you can obviously see that at this point, at the bottom we are going to see compression, and at the top we are going to see tension. So, therefore, we will have tension at the top, compression at the bottom. So, in both the cases we see that we are going to have tension at the top and compression at the bottom, and the stresses are tension at the top and compression at the bottom. So, that is why the stresses are both positive. Now, we will try to consider the case of a simply supported plate. Let us see the other extreme. When the plate is simply supported, what happens? Again, we are trying to look for the case when capital P is 0 and small p is not equal to 0, and in the case of the simply supported plate, we would have conditions like at x is equal to a, at the outer edge of the plate we will have deflection equal to 0 and bending moment equal to 0. A bending moment in the circumferential direction will be 0. So, m1 equal to 0, and we are going to get the slope at the center of the plate to be 0. So, we can now write the boundary conditions. Phi equal to 0 at x is equal to 0, then W equal to 0 at x is equal to a, and bending moment equal to 0, bending moment of course m1 equal to 0 at x is equal to a, and our case is capital P is 0 and small p is not equal to 0. We proceed as before. In this case, we start with this expression of W. W is equal to Px4 64d minus C1 by 4 x square minus C2 ln x plus C3, and now we can write phi minus dw dx is equal to minus pxs cube by 16d minus C1 by 2x minus C2 by x. The slope, as we have slope equal to 0 at x is equal to 0. So, phi equal to 0 at x is equal to 0, and that means this term is going to shoot to infinity. Therefore, this constant must be equal to 0 to have finite value of the slope. Finally, therefore, we can now make use of the condition that W equal to 0 at x is equal to a. So, we have now we will just substitute w equal to 0 at x is equal to a, noting that we have already got C2. So, therefore, this is going to be PA4 64D minus C1 by 4 A square plus C3 equal to 0. So, this is equation number 1. We have two constants involved. Now, we can make use of the other boundary condition provided we have the expression for bending moment m1. So, if we consider bending moment m1, which is d into d phi dx plus nu times phi by x, and therefore, d phi dx is equal to minus 3 p x square by 16d minus C1 by 2, and hence we can now write d m1 as d into 3p x square by 16d plus C1 by 2 minus nu times phi, which is phi by x. Of course, we have p x square by 16d nu C1 by 2, that is the value for m1, and since m1 is equal to 0 at x is equal to a, so this of course we can write in a neater form, because this d is going to cancel for these two terms. So, therefore, we can write now 3 plus nu by 16 p x square plus 1 plus nu by 2 C1 into d, and since m1 equal to 0 at x is equal to a, we now get equation involving C1 like this. And therefore, we get C1 equal to 3 plus nu by 8 into 1 plus nu into d p a square. And if we get back to earlier equation 1, which is here, from that equation substituting the value of C1, we can now obtain C3. So, therefore, C3 is equal to minus PA4 by 64D plus A square by 4 C1. So, therefore, it will be 3 plus nu by 32 into 1 plus nu into d PA4, and that gives us 2 into 3 plus nu minus 1 plus nu by 64 into 1 plus nu d p a to the power 4, which simplifies to PA4 64D 5 plus nu by 1 plus nu. So, we can now substitute the value of C1 and C2 and recover the expression for deflection and slope. So, let us now again put the values back and get the expression for W. W is equal to Px4 by 64 d minus 3 plus nu 32 into 1 plus nu d p a square x square plus 5 plus nu by 64 d into 1 plus nu p raised to the power 4. And you can see that the maximum deflection of the plate is going to occur at x equal to 0, and the value of the maximum deflection is given by this expression. So, in this case the maximum deflection is going to occur again at the center, and this maximum deflection is equal to 5 plus nu 64 d 1 plus nu p a is to the power 4. And the value of phi is now p x s cube by 64 d plus 3 plus nu 16 1 plus nu into d p a square into x. So, that is the value for phi. And if we calculate m1, which is m1 is nothing but d into d phi dx plus nu phi by x. So, we have everything. So, if we substitute, the expression for m1 turns out to be m1 is equal to 3 plus nu by 16 p x square plus 3 plus nu by 16 p a square. So, this has a simplified form 3 plus nu by 16 p a square minus x square, and hence value of maximum bending moment is equal to 3 plus 16 3 plus nu I am sorry 3 plus nu by 16 p a square. Similarly, if we calculate m2, which is nothing but d into phi by x plus nu times d phi dx. So, d phi by x plus nu times d phi dx. Once you do the substitution in this, we get m2 minus p x square 16 d plus 3 plus nu 16 1 plus nu d p a square plus nu times d phi dx (3 plus nu by 16 1 plus nu d p a square. So, it is 3 plus nu by 16 into 1 plus nu p a square by 16 1 plus nu into d, and this gets simplified a square 3 plus nu x square 1 plus 3 nu, this expression, and hence M2 maximum is at x equal to 0, which is p a square by 16 into 3 plus nu. So, finally, we have been able to get the maximum of both the moments. M1 maximum we have got already 3 plus nu by 16 p a square. M2 maximum is also of the same magnitude, and hence now we have at x equal to 0 sigma 1 max is equal to, it is nothing but 6 times the moment divided by h square, and therefore, that will become 3 plus nu p a square by 16 h square, and this is 3 by 8 3 plus nu p a square by h square. And in fact, the stress in the circumferential direction is also the same. So, therefore, sigma 2 maximum is also of the same magnitude. You can think physically also to establish that sigma 1 maximum is equal to sigma 2 maximum. We can consider the plate this is the center of the plate, and we have seen that at this center sigma 1 max is equal to 3 by 8 3 plus nu into p a square by h square. If you consider that this is the direction of sigma 1, which is a radial direction. Now, the perpendicular direction is this one, this is also a radial direction, and since it is axisymmetric, the stress in this direction, which we indicate to be sigma 2, it has got to be equal to sigma 1, and hence at the center the stress in this direction is maximum. So, also it is going to be maximum in this direction, and hence sigma 1 maximum is equal to sigma 2 maximum. The picture is not different in the case of clamped plate as well, only the boundary condition will change, but at the center we will have again sigma 1 maximum is equal to sigma 2 maximum. For the case of simply supported plate and also for the case of clamped plate, we can find out the stress variation along the radius and they can be compared. We will compare this in our next lecture.